Okay, so we'll begin with kind of these questions on whether any of these conditions for the central limit theorem have been met or violated. This is the practice final, right? So this was your homework this past week. So I'm just going to kind of work through the practice final is what we'll do today. Okay, so it says a study is performed to understand the relationship between bright lights and headaches, and it says we have randomly selected subjects and randomly selected subjects, so independent and random seems to be met, okay? And then here and we look at our sample size, and we have 80 randomly selected subjects exposed to bright lights, and 90 randomly selected subjects are exposed to less bright lights. Okay, so our sample sizes, so N1 is 80, and N2 is 90. Okay, now so for the big population condition, 10 times 80 is 800, and 10 times 90 would be 900, okay? And the entire population would be all people who can be exposed to bright lights, all right? And that would be like a lot of people, right? So it's much more than 800. So all people who can be exposed to bright lights and all people who can be exposed to, less bright lights. To bright lights, and then this would be, basically all people who can be exposed to other lights, right? So those populations are going to both be huge. Okay, so big population condition, that's going to be met. Okay, and then lastly we have the large sample condition. The large sample condition, either n times p has to be bigger than 10 and n times 1 minus p has to be bigger than 10, or in this case we need to have at least 10 successes and at least 10 failures. Okay, so over here we have 20 who have headaches. So for sample we have 20 with headaches, and that means 60 because the sample has a total of 80 people, right? So 80 minus 20 is 60 have no headaches. And then over here we have 12 with headaches, and that means 90 minus 12, or 78, have no headaches. Okay, so large sample condition is also met because we have at least 10 successes and 10 failures. So far, so good? Great. All right, let's try the next one. so these are all in your okay, so for this one, let's see. Confidence interval for a certain disease, he finds 300 randomly selected subjects. Okay, so the random condition is met. Okay, big population. All right, so the population would be all people. Okay, because we want to know how prevalent a disease is, period. So this would just be all people. So there, there's billions, right? So that's definitely big enough. Okay, so as far as large sample goes, both n times p and n times 1 minus p have to be bigger than 10. So n times p would be 300 times 0.02, that gives me 6. Okay, and n times 1 minus p would be 300 times 1 minus 0.02 is 0.98. That gives me 294. Okay. All right, so 6 is not bigger than 10. So this is large sample condition is violated. All right. Number 3 says a student has to conduct a survey for a school project. He goes around the school campus and interviews people he meets. He finds data from 100 people and finds that 45 of them answered yes to his questions. Are any conditions violated here? Yeah, it's not random, right? He's just going around the school and interviewing people he meets. This is not random. Okay. I mean, sometimes it feels like the people we meet in a day are random, but they're not, okay? They have to at least be out of the house, which means you're not going to meet people who stay inside the house all day. Okay, so I mean, so that's going to be violated. As far as people, the population would be. It doesn't even say what the relevant population is, because I mean this is just not random, so we got all sorts of problems there. Okay. All right, company wants to survey its employees. It has 800 employees, so this is our population here. The population is the 800 employees. And then it selects 100 of the employees at random, okay? So here, 100 times 10 is 1,000. And this is going to be, our population is not big enough. Okay.
What about the large sample?
So we didn't get any information about whether or not how many successes there were. So we can't answer the question. I should have written a little bit more in this question, yeah, I didn't write how many successes or failures there were when they surveyed, so we don't have information about the large sample condition. Okay. Yes.
I have a question about number 1, please. I didn't see what the answer was.
Okay, so the number 1 was no conditions were violated.
None at all.
Yeah, none were violated.
Okay, thank you.
Yes, and no.
The population has to be close, you said 10,
I'm sorry?
to be big enough, the population has to be.
At least 10 times bigger than the sample. So here the sample was 800 employees. Our population needs to be at least, our sample was 100 employees. 100 times 10 is 1,000. So the population needs to be at least 1,000. There's only 800 people. So that means we should really only sample like 80 people. Yeah, Raphael.
I don't need to keep you jumping back and forth.
That's fine.
On number 1, we said 10 successes and 10 failures.
Yes.
There's no, clear-cut like success and failure procedures. So if I wanted, can I just make it simple for myself and do the large sample formulas?
Well, I mean, so we 20 experienced headaches. That it's a funny label to say success, but basically either you have headaches or you don't. So you need to have at least 10 who do and at least 10 who don't. So we have 20 who have headaches and 60 who don't. So both of those numbers are bigger than 10, so that's okay. And then as far as the other one, we have 12 who have headaches and 78 who don't. So both of those numbers are bigger than 10. So there's no here. P was not given. Okay, in question 2, P is given. So you do n times P and n times 1 minus P. But in some cases, P is given, and in other cases, a count is given. And depending on those, you have to check either n times P to kind of get a count to see if that's bigger than 10, or you just see if the count itself is bigger than 10. Yeah.
Can you dim the front lights just a little bit?
Oh, yes.
Thank you.
It was good for a second.
For a second?
Yeah.
Okay, there we go. Yeah. Yeah, before artificial lighting, you just go to bed when it got dark, right? And hope those nocturnal animals wouldn't hurt you. Okay. All right. So we'll keep it going. Okay, so it says a farm wants to test 2 different diets for their cows to see which diet causes more weight gain. They randomly select 10 cows to give diet 1, 12 cows for diet 2. After 2 weeks on diet 1, the cows gained an extra average of 15.2 pounds, standard deviation of 4.1. 2 weeks on diet 2, 12 cows gained an average of 12.6 with a standard deviation of 3.4. We're looking at a confidence interval for the difference in average weight gain. Okay, so we want to know, are we dealing with means or proportions? Okay, we've got means. And do we have 1 sample or 2? 2 samples. Okay, and so this will guide how we're going to do this. And we're dealing with a confidence interval, all right? And so there's a few ways we can, approach this. Is, there's that formula sheet posted online. Let's see, is that right here? Yeah. So there's the formula sheet, and then there's also the study guide, or the kind of guide for inference. And I created these both with the intention that they would be helpful. Let's see there. So but if you have your own way to approach these problems, that's also entirely fine. Okay, but anyway, we've got confidence intervals, means, 2 samples, and it says kind of this is what we've got. So x bar 1 minus x bar 2 plus or minus t star times the standard error. So we've got, let's take a look. We've got x bar 1 minus x bar 2 kind of plus or minus t star times the standard error. This is going to be our confidence interval. And so let's go through the problem and try to pick out all of these pieces here. Okay, so it says 10 cows were given diet 1. So we've got sample 1 and we have sample 2. Okay, so we have N1 is equal to 10, and it says 12 cows for diet 2. So N2 is 12. The average of 15.2, this is going to be x bar 1. And x bar 2 is going to be 4.1. Oh, you're right. Sorry, I'm not. S1 is 4.1. Sorry. Thank you. And then X bar 2 is 12.6, and S2 is 3.4. Thank you. It's embarrassing. Okay. Huh? Yeah, well, so anyway, I was going to say it's important that we label these things correctly. Otherwise, you know, we might make a mistake when we plug them into the formula, okay? But yeah, so go through and, you know, just make sure you label your numbers correctly so that when you plug them in, you'll get the right answer. Okay, so anyway, the center of the interval is always the part that comes before the plus or minus. So as far as number 5 goes, the center is going to be x bar 1 minus x bar 2, which in this case is 15.2 minus 12.6. So at the center of our interval, we have 2.6. Okay. Number 6, what value do we use for t star? Okay, so we have to figure out our degrees of freedom, and we're going to use n minus 1 degrees of freedom, and we only have, our smaller n is 10, so degrees of freedom is n minus 1. Using the smaller n, we have 10 minus 1, so we have 9 degrees of freedom. Okay, 9 degrees of freedom, and at 95% confidence, our t star is going to be 2.262. Okay. 7 is asking for the standard error. This is just a matter of plugging in values into our formula. S1 squared over N1 plus S2 squared over N2 okay, so we just plug in, what do we have, 4.1 squared over 10 plus 3.4 squared over 12, okay, and we get 1.626. Okay, I'm hoping everybody can use their calculator by now, but you know, if you're having trouble with the calculator, then I guess I can show you what buttons you should push. So let's see. So I would, you know, you'd hit square root. So there's a few ways you can do this. You can put this all, you can do the square root, or you can do the inside and then take the square root, okay? So if you're gonna put it in one step, you have to just make sure you're using your parentheses correctly. So I got 4.1 squared over 10 plus 3.4 squared divided by 12, and close off the parentheses, okay? And I get 1.626. All right. Okay, and then so for number 8, we're going to just plug in the values into this. And so I have 2.6 x bar 1 minus x bar 2 plus or minus my t star, which is 2.262, times the standard error, which is 1.626. Okay, and when I do that on my low end, I get negative 1.78, 0.78, and on the high end, I get 6.278. And so that's what I'm getting when I punch all of this in. So far, so good? Okay, and then so number 9 is asking, do you conclude that there is a difference in the average weight gain? Okay, so how do we just make this decision? We want to know, is 0 inside the interval?
Yes.
Okay, so 0 is inside the interval, and so that means what? Yeah, so 0 is a plausible value for the difference, meaning it's plausible that the difference between them is 0 or that there's no difference, okay? So 0 is in the interval. Okay, so it is plausible that there's no difference. When you're dealing with two samples, okay? So yeah, when you're doing a confidence interval for mu1 minus mu2, you're looking for 0. For the other ones, you're looking for the value specified. Okay, so I think like later on we have like a problem on pants or jeans or something. That one you're looking for that number specified. Okay, so it is plausible that there is no difference. Or in other words, we do not have evidence that there is a difference. I have to... Okay. And then as for number 10, if we made a 90% confidence interval instead, how would that compare? The 90%, we would use a different t-star value, and so our confidence interval would be narrower. Okay. And that's kind of how confidence intervals work. If you want to be more confident that you've managed to capture this unknown value of the parameter, you have to kind of cast a wider net. Okay, so you need a larger confidence interval. If you're willing to be less confident, you can have a smaller interval. Okay, and having a smaller interval is nicer because it kind of gives you a more precise answer, but you're going to be less confident in that answer. Yes.
So for number 8, how do you want the confidence interval formatted? Are you okay just with the low and the high?
Yeah, so it's going to be multiple choice, right? So you'll have to look. So I mean, one way I could present it is like this: negative 1.078 to 6.278. This is one way it can be written. It's just kind of low to high, and kind of like a pair of numbers indicating this is the low end and that's the high end. Okay, so that's one way to present the values.
What's the last word?
Narrower, less wide. Okay, is that all right? Number 10? Good? I'm going to move on here. Okay, so I've got at the ruler and yardstick factory, a machine is suspected to be defective. The yardstick it produces are supposed to be exactly 3 feet long. You measure a random sample of 40 yardsticks and find that the average length is 3.02 with a standard deviation of 0.03 feet. Is this evidence that the machine is producing yardsticks that are too long? Okay, and so here we're talking about a hypothesis test. Okay, but first of all, we should decide, are we dealing with means or proportions here? Okay, we're dealing with means, and we know this because it gives us a standard deviation, and we're talking about the length of a yardstick, so it's a numeric variable. Length is numeric. Okay, so we've got means, and then how many samples do we have? One sample, okay. And it's a hypothesis test, exactly, all right. So it asks, is this a one-sided or two-sided test? So we look at the question and it says, is this evidence that the machine is producing yardsticks that are too long, okay? So here, too long indicates that we're just worried about the one side, okay? We're not asking if the yardsticks are different. So number 11 is going to be a one-sided test because it says too long. The key word here is, are they too long?
If it had said too long or
Yeah, if they,
splintery or something.
or it says is this evidence that the machine is producing yardsticks that are not exactly 3 feet? Then it would be a two-sided test. Okay, because then not exactly 3 feet would be too short or too long would both be problems here. Okay, which is actually probably the more realistic problem at the yardstick factory, but yeah, in this case, the question was, are they too long? Apparently, short yardsticks okay, but too long yardsticks, we can't have that. So, okay. Did you have a question, Raphael?
You're talking about details, right? Like
Yeah.
Different would be two-sided and
Different would be two-sided, so a not equal sign, and the alternative would be a two-sided test, whereas greater than or less than would be a one-sided test. Okay, so number 12 says, what would our hypotheses be? So here, our mu would be the length of yardsticks that the machine is producing. Okay, and then we want this to be exactly 3 feet. Okay, and then the alternative is we're worried that the machine is producing yardsticks that are too long, so we're going to have mu is what? Greater than 3 feet. Okay, and we're using 3 because this is the value that we're like expecting, and not the value from our data. Okay. 13 asks for a test statistic. So before we do that, let's kind of just list off the values that we have. What is our sample, our n? 40. We got 40 yardsticks. What's our sample mean, x bar? 3.02. And what's our standard deviation? 0.03. Okay. So here it's asking, what's our test statistic? Okay, so our standard error is going to be 0.03 divided by the square root of 40. And we get 0.004743. Okay, and then the test statistic is going to be the difference between x bar, our mu 0 from the null hypothesis divided by our standard error. So here I've got 3.02 minus 3 divided by the standard error. Okay. So here on my calculator, I'm going to just type this in, 3.02 minus 3 in parentheses, and I'm going to hit divide by the answer key because the standard error is already in my answer. I'm going to hit equals there, and I get 4.216. So this is my test statistic, 4.216. Okay, so now we're going to look up 4.216 in the T table. So let me actually download our T table. Here we are, reference tables. Yeah, we will use 30 degrees of freedom because we always round down. And where are we? Okay. So at 30 degrees of freedom, we're going to look for 4.216, and we see that it's larger than the last number there, 3.385. It's larger than this. So that means the corresponding p-value will be smaller than 0.001, because when we look at the column headings, they go smaller as we go to the right. So our so 4.216 is larger than the last value. larger or to the right, or I'll just say, yeah, to the right of the last value in the row. Okay, so our p-value is less than the column heading 0.001. Okay, so we would just write p-value is less than 0.001. Okay. So if our alpha is 0.05, what's our conclusion? Yeah, alpha is 0.05, our p-value is less than alpha, we would reject the null hypothesis. So what does that mean? We have evidence that the machine is producing yardsticks that are too long. Okay. Okay, and then lastly, if the conclusion we just made was wrong, what kind of mistake is that? Type 1, right? So, because our conclusion was to reject, if that was a mistake, if our conclusion to reject was wrong, that's a type 1 error. Yes. Question? Number 14, yeah.
Yeah, looking at what do you mean by it's larger to the right of the last value?
Okay, so when you go to the t-table, we're looking at 30 degrees of freedom, right? Our test statistic is 4.2. Okay? If we had to kind of fit 4.2 in this thing and we're comparing it, 4.2 is larger than 3.385, okay? So if somebody said, you know, put this where it belongs, you would put 4.2 over here. Okay? And so it's to the right of 3.385, which means when, as far as column headings go, it would be over here, which means less than 0.001. Yeah, so the numbers, the test statistics get larger as we go to the right. The column headings get smaller as we go to the right. So that's what we have going on. Okay, good? All right, it says researchers believe that 15% of the population is left-handed. I'm sorry, 14%. A local school decides to see if their students have a different proportion of left-handed people. The school has a total of 1,500 students, and they randomly select 90 students for the study, and they find that 15 of them are left-handed. Is this evidence that the proportion of left-handed students at the school is different from the population proportion? Okay, so first of all, are we dealing with means or proportions? Proportions, and do we have one sample or two? We only have one sample, okay? Because as we're trying to read the problem, we see that there's only one n, and what is that n? N is 90, okay? We got 90 students in our sample. 1,500 is our population, but that's not our sample, okay? So n is 90, x is 15, and then so our p hat is 15 out of 90, which is like 0.1667. I don't know, something like that, I think. 15 divided by 90, yeah, 0.166, so on. Okay, so my sample proportion p hat is 15 out of 90. That's what we have there. Okay, we're going to make a 90% confidence interval. So what is the critical value z star we would use? 1.645. That's just a given. Anytime you're going to do confidence intervals for proportions, there's just 4 values you need to know. And for 90%, that value is 1.645. Okay. As far as number 19 goes, what's our standard error? So you can look at the formula sheet, or you can look at the study guide or whatever, and then it says for the confidence interval, it's going to be p hat times 1 minus p hat over n. Okay, so here we're going to use 0.1667 and 1 minus 0.1667. Okay, we're not using 0.15. So I'm going to hit square root of answer times parentheses 1 minus the answer. Okay, because I've got basically 0.1667 whenever I hit answer. And then divide that by 90, close off the parentheses, and I get 0.039283, so 0.0393. Okay, what goes as the center of the confidence interval? All right, the center of the confidence interval, if we create our confidence intervals p hat plus or minus z star times the standard error, it's whatever's in front of the plus or minus, so our center of the interval is just p hat, okay? And we've already established that to be 0.1667. So that's number 20. Still good? Okay, so 21, make your confidence interval. So now we're going to just plug in the values into p hat plus or minus z star times the standard error. So I got 0.1667 plus or minus 1.645 times 0.0393. Okay, so let's just see what happens. Okay, so I'm going to multiply this times 1.645. Okay, so my margin of error is 0.0646. And I got 0.1667. So the confidence interval I end up getting is 0.1021 to 0.2313. So if you look at the formula for a confidence interval, it's p hat plus or minus z times the standard error. The center of the interval is always the part before the p plus or minus. Okay, so our center is going to be p hat. Okay, or you know if you I have the guide for inference. So you know some people prefer the formula sheet because it's just kind of straightforward. Okay, as far as the guide for inference, I kind of broke down all of these things. So, you know, what is the center? The center is the part that goes before the plus or minus for one sample proportion, which is the situation that we have. It is the sample proportion, the p hat. So it's also spelled out for you here. Okay. So it's
So for 21,
uh-huh.
0.0646, you got that by...
I did 1.645 times 0.0393.
Okay.
That's my margin of error.
Okay.
Okay. So I could have asked, you know, what's the margin of error, and you'd tell me it's 0.0646. Okay, and then based on our interval, is this evidence that the proportion at the school is different from the nation? So what are we going to do to answer this question?
14%.
Yeah, we want to know, is 14% inside the interval? And it is. Is 14% in the interval? Yes. Our interval goes from basically 10% to 23%. So 14% is in the interval. So it is a plausible value for the school. Okay. So so we do not have evidence that the nation's proportion, so we do not have evidence that the school's proportion is different from the national proportion of 14%.
And you got the point 1021 to point 2313. How'd you get that margin?
I did 0.1667 minus 0.0646, and I got point. Okay. So okay, so here I write, so we do not have evidence that the school's proportion. Yes.
I'm sorry, this is so dumb, but how did you get Z star again?
There's just 4 values that you kind of need to memorize or know. Okay. Right, exactly. Okay, and those are all listed on your formula sheet and the study guide if you choose to use either of those. Okay, so you know on the formula sheet it says Z star values. These are the 4 that you need. Okay, and then on the study guide, what is the critical value? They're also listed right here. Okay, so they're all there. You know, I'm biased. I think the sheets I've made are pretty good, but you know, if you're more comfortable, you know, like for some people, writing their own formula sheet is like part of the learning thing. So if you want to do that, you can do that. Just make sure you have all the things you need. Okay. Okay, we'll keep chugging along here. All right, so it says you buy a bag of Starburst candies. This is the and we want to know, is there a difference in the proportion of cherry flavored candies? Okay, so you got Starburst and Jolly Rancher, and you know, does one brand have more cherry flavored candies than the other? All right, so are we dealing with proportions or means here? Proportions, right? Because we want to know, are they cherry flavored or not? That's a categorical variable. Okay. All right, and then we've got 2 samples. We've got Jolly Ranchers and Starburst candies, okay? Okay, so here I'll list off the data that we have. Sample 1 will be Starburst. And sample 2, okay, or group 2 will be the Jolly Ranchers. Okay, so our N1 is 80. And our x1 is 12, which means my p hat 1 is 12 over 80, 15%. Okay. For sample 2, the Jolly Ranchers are N2. We have 70 pieces. And our x2, we have 14 cherry candies. And so our p hat 2 is 14 over 70. We got 20% cherry candies for the Jolly Ranchers. Okay, and we want to know, do we have a different proportion of cherry-flavored candies, and we're dealing with a hypothesis test. Okay, so 23, let's write out the hypotheses. So what are we going to write for our hypotheses? Yeah, P1 is equal to P2. Okay, and again, if you're not sure about these things, I have these listed out here. All right, so we've got hypothesis test proportions 2 samples. It says the null hypothesis right here. P1 is equal to P2. Okay, and I think over here I've got for two sample proportions, oh, I wrote it out in the other form, P1 minus P2 is equal to 0, okay? But those are the same thing, right? Okay, so yeah, we could also have the null hypothesis being P1 minus P2 equal to 0, all right? And then the alternative hypothesis, we want to know, are they different? So we would say P1 is not equal to P2, or vice versa, P1 minus P2 is not equal to 0, all right? So either way you've written these, they're saying the same thing. Yes?
Where did you get the proportion one, the p-hat one?
P-hat 1 is just 12 divided by 80, right? So you take the number of cherry candies out of the sample size. And then over here, for P-hat 2, 14 divided by 70 is P-hat 2. Okay, the proportion for that sample. Okay, 24, it says, what is the value of P-hat? P-hat is our overall proportion. So that's x1 plus x2 divided by n1 plus n2. So here we have a total of the total number of cherry candies that we have, which is 26, out of the total number of candies we see, which is 150. 26 out of 150, 17.1733. Okay. Number 25 is our test statistic. So there's a few parts. First, we got to figure out our standard error, which is p-hat times 1 minus p-hat over 1 over n1 plus 1 over n2. Okay, this is all written on the formula sheet. Or if you want to memorize it, that's fine too. And then, so this is just plugging in our values, 0.1733 times 1 minus 0.1733 times 1 over 80 plus 1 over 70, okay? So this times 1 minus that times, parentheses, 1 over 70 plus 1 over 80. Or 1 over 80, yeah. I have them backwards, but addition is commutative, so. Okay, and I get 0.06195. That's our standard error. So, but that's not our test statistic, right? Our test statistic is p-hat 1 minus p-hat 2 divided by our standard error. So here that's 0.15 minus 0.2 divided by 0.06195. And with that, I get negative 0.81. Because I think if I do that, 0.15 minus 0.2 divided by my standard error, yeah, negative 0.81. What's that?
It's the rounding that always happens.
The rounding always throws you off?
I was saying just 1%.
Okay. Yeah, when you have to look up a z-value in the table, you have to round to 2 decimal places. So that's our 25. Our test statistic is z equal to negative 0.81. Okay? And then so for 26, we want to find our p-value. So for our p-value here, we're going to find the tail area, which in this case, because z is negative, it's just going to be the area to the left, which is the area in the table. And then we're going to multiply that by 2, right? So we look up z equal to negative 0.81. Okay, and I look up z equal to negative 0.81 and I get 0.2090. So area to the left of z equal to negative 0.81 is 0.2090, okay? But the p-value, because I have a not equal sign, I'm going to multiply it by 2. So my p-value is 2 times that, which gives me 0.4180. Okay, and so what's the conclusion we make? If my p-value is 41.8%, I'm not going to reject the null hypothesis. So 27, do not reject the null hypothesis. Okay, and what does that mean? That means we don't have evidence that there are different proportions of cherry-flavored candies in Jolly Ranchers and Starburst candy bags. So, because our p-value is too big, right? So it's saying if these were just random samples, right? You tear open a bag of Jolly Ranchers and you go, how many cherry candies? I don't know. You have an obsession with cherry or whatever, and you know, how many cherry-flavored candies did I get? You know, you get 20% of your Jolly Ranchers are cherry-flavored. And then for the Starburst, 15% are cherry flavored. You know, is that evidence that there's a difference at the factory? No. Okay, not at this point. You know, maybe if you buy thousands of bags and you get 20% consistently for the Jolly Ranchers and 15% consistently for the Starburst, then maybe you have evidence that there's a difference, but not with just this small sample. Okay, going on to the next set of problems here. All right, so here it says researchers want to know if drinking caffeinated drinks improves reaction time. Certainly seems that way in the morning, right? Yeah. Okay, so, and then it says they randomly select volunteers in a blinded experiment, gave some of them caffeinated drinks and others non-caffeinated drinks, and then they record reaction time, okay? And it says these people got caffeine and they had this was their reaction times, and it says these people didn't get caffeine and this was their reaction time. So, there were actual tests, and I just kind of altered the data to simplify it for our class, but you know, they did, the conclusions of the findings, I think, matched up, but yeah. All right, so how many, are we dealing with means or proportions? Means. Okay, and how many samples? 2 samples, right, okay. So we have means and we got 2 samples, and let's look at sample 1. Okay, this will be those with caffeine, right? They got 300 milligrams of caffeine. Our sample size, N1, we have 30 people. The average reaction time, X bar 1, is 580. And the standard deviation here is 110, okay? And then sample 2 is the no caffeine group. And N2 here was 25 people. The average reaction time of these 25 people was 640 milliseconds, and the standard deviation here is 130. Okay? And we want to know, is this evidence that drinking caffeine improves reaction time? Okay? So 28 asks, what would our hypotheses be? So 28 says what our hypotheses would be. So the null hypothesis would be that they are equal to each other, right? mu1 is equal to mu2. Yeah, question?
Are you going to give it like that on the final, like group 1, group 2?
Yeah, I'll probably list it out like this, okay? But I won't list it out like this. You got to label this, okay? All right. What does it mean to have improved reaction time? Should we have mu1 greater than, less than, or what?
Less than. It's faster.
Yeah, we want less than mu2, mu1. So if we think about reaction time, okay, improved reaction time means it takes you less time to react, right? The amount of time it takes for you to react is less than someone else, okay? So that's going to be improved.
But wait, isn't one the caffeinated one?
Yeah, so sample 1 is the caffeinated group. So they got the caffeine, And so we're expecting them to have better reaction times.
Oh, which is then what?
Better reaction times mean it takes them less time to respond, okay? So just because it says something like improve doesn't mean we want the numbers to be bigger, okay? So things like reaction time, improved or better reaction time means it's a smaller number, right? All right, the observed difference in means. What's our observed difference? Yeah, it's going to just be the difference between x bar 1 and x bar 2, which is 580 minus 640. So we're getting a difference of negative 60 milliseconds. Okay. All right, number 30 asks, what's our test statistic? Okay, so first we got to figure out our standard error, which is going to be 110 squared over 30 plus 130 squared over 25. I punch that out and I get 32.85. Okay. And then as far as the test statistic goes, that's going to be x bar 1 minus x bar 2 divided by our standard error. So I get negative 60 over the standard error, and I get negative 1.826 for number 30. Okay? So 31, we're going to look this up in the t-table to get our p-value. Okay? So the degrees of freedom we're going to use is n minus 1. So that means we're going to use the smaller n. We're going to have 24 degrees of freedom. And so I'm going to look up negative 1.826 in 24 degrees of freedom. So 24 degrees of freedom, negative 1.826. That's in between this column, 1.711 and 2.064, which means the corresponding tail is between 0.05 and 0.025. Is that good with everybody? Okay. So my tail area is between 0.025 and 0.05, okay? Do I just leave it at that, or do I double it from my p-value? Just leave it, right? Just leave it. Okay, so my p-value, so I'm gonna write my p-value is between 0.025 and 0.05 in this form, okay? But, I mean, that's saying the exact same thing. The p-value is greater than 0.025, but less than 0.05. Yeah, question?
Yeah, isn't the degrees of freedom n1 minus n2?
No, degrees of freedom is n minus 1.
Oh, n minus 1.
Yeah, degrees of freedom is always n minus 1.
The small
And then when you have two samples, you take the smaller n. Okay? Okay, so my p-value is between this and this. All right, and if number 32 says if alpha was 5%, is my p-value bigger or smaller than alpha? Smaller than alpha. So p-value is less than alpha, which means we reject the null hypothesis. And that means we have evidence that caffeine improves reaction time. Okay, and then lastly, 33, if that mistake to reject the null hypothesis was wrong, what kind of mistake is that? Type 1 error. Huh? So it's saying if that conclusion was a mistake. So the conclusion we did was reject the null hypothesis. If we mistakenly reject the null, that is type 1 error. Okay? Yeah, 1.826 is not on the chart, but it's in between So if you look at 24 degrees, huh? So if we had to fit, you know, we're looking at this row for 24 degrees of freedom, right? So we're looking at 24 degrees of freedom, and we're going to say, okay, 1.826, you know, if you had to place it in this row so that, you know, it kind of fits the order, you would put it after 1.711 because 1.826 is bigger than 1.711, but it's smaller than 2.064. So we would put 1.826 in between these two columns. Okay, and then so that means the corresponding tail area is in between the column headings of 0.05 and 0.025. So we don't know the exact value, but we do know that it's in between 0.05 and 0.025. Okay. All right. 34 through 39. So here it says, in a certain city, a study was conducted to see if the police department and fire department had a different proportion of minority employees. Okay. So they randomly select 200 employees from both the police and fire departments and took note of whether or not they were a minority. Okay. So then, yeah, we got proportions and we have 2 samples. Okay, so let's kind of list off what we have. So sample 1 will be the police. And sample 2 will be the fire department. And N1 is 200. We had 200 people over here. And the number of minority employees was 80. So our P hat 1 is going to be 80 over 200, 40%. And then for the fire department, 200 employees, 50 of them were minorities, so our P hat 2, 50 divided by 200, 25%. Okay, and then, so for 34, what are the hypotheses? We have 2 proportions, and it's a hypothesis test, so our null hypothesis is that P1 is equal to P2, or that the difference between them is 0. And then the alternative, we want to know, do they have different proportions? So here we're going to have P1 is not equal to P2. 35 is our overall proportion. What's the value of P hat? So we're going to do x1 plus x2 over n1 plus n2. And we do 80 plus 50 divided by 200 plus 200. So we have a total of 130 people out of 400 people who are minority employees. So that gives us a proportion of 0.325. Okay, so number 36 asks what our test statistic is. So first we're going to have to figure out our standard error. That's going to do P hat times 1 minus P hat times 1 over n1 plus 1 over n2. And if I did that correctly, I'm getting 0.04684. And then so my test statistic is the difference between P hat 1 and P hat 2 divided by our standard error. I'm getting a difference of 0.4 minus 0.25 divided by 0.04684. And I get a z-score of 3.20. Okay, so then 37, we want to know the p-value. So here I've got a two-sided test, so I'm going to look up 3.2, and I want the tail area, which is the area to the right of 3.2. Okay, so the tail will be area to the right of 3.2, because if you have a positive z, you want the area to the right. So the area to the right of 3.20, oops, is 1 minus 0.9993, which is 0.0007. Okay, and so my p-value is 2 times that. And that's going to be 0.0014, 37. Okay, what is the conclusion we make? Well, this thing is less than 5%, so we are going to reject the null hypothesis. Our p-value is less than 5%. That means we reject the null hypothesis. We have evidence that the proportion of minority employees is different. Okay. And then 39 says, in the context of this problem, what does it mean to commit a type 1 error? So 39, to commit a type 1 error means the null hypothesis is true, but we believe that it is false. So the null hypothesis being true means the proportion of minority employees is the same for both departments, okay? So so a type 1 error would be both departments have the same proportion of minority employees, so I'm just going to write same proportion, but our conclusion is that they are different. But we conclude okay. So in reality, the proportion is the same for both fire departments and police departments. They both employ the same number of minority employees, or not same number, but same proportion of minority employees, but maybe the public or whatever doesn't believe that, or something like that. That would be a type 1 error. Okay. And so sometimes we ask, like, which error is worse, type 1 or type 2 error? And I know that was in, like, the practice quiz. So in some cases, like, we don't know which type of error is worse. And that might be a matter of opinion. But I think, on the quiz, and if I were to have a question like that on the exam, it would be very clear, right? Yes?
So do the type errors sort of inform whether you pick the right p-value or not?
The type of errors should inform your decision of an alpha, okay? Because we actually get to choose alpha. We get to choose, we often default to a 5% alpha, but it doesn't always have to be 5%. And if you want to use a larger alpha or a smaller alpha, that's your decision as the one doing the research, okay? And so yeah, we may decide we want a larger alpha, or we may decide we want a smaller alpha, depending on the types of mistakes that correspond with the type 1 and type 2 error. Yeah?
So for number 39, could you write down what would be a type 2 error? Would it be that both departments have the same proportion of minority
It would be, so type 2 error would be that in reality the departments have different proportions, okay? But we don't come to the conclusion that they have different proportions. Okay, we would never actually come to the conclusion that they have the same proportion, but we don't come to the conclusion that they are different. So in reality, they are different, but we don't come to the conclusion that they're different. That's a type 2 error for that problem. Okay, so in this one, it says potatoes are sold at the grocery store in 5-pound bags. You decide to weigh a random selection of 10 different bags, and you find that the average weight of these bags is 5.2 pounds with a standard deviation of 0.3. Is this evidence that the bags at the grocery stores have a mean weight different from 5 pounds? Okay, so yeah, we got means, and it's one sample. Confidence interval, exactly, right? Okay, and then so our n is, how many bags did we look at? 10. Why don't I see this on my screen here? Oh, it's first line. Sometimes my eyes play tricks on me too. Okay, so n is 10, and then x bar is 5.2, and s is 0.3. Okay. How many degrees of freedom? 9. Degrees of freedom will be 9. N minus 1. N minus 1 equals 9. Okay. The center of the interval. So we got x bar plus or minus t times the standard error, and the standard error is s over the square root of n. Okay, so x bar is the center, and that's going to be 5.2. 42, what's the standard error? That's going to be s over the square root of n. 0.3 divided by the square root of 10. And I get 0.0949. Okay, and then so 43, what is the resulting confidence interval? 5.2 plus or minus, we're going to have to look up 9 degrees of freedom, 95% confidence, I think that's 2.262, times our standard error of 0.0949. Huh? You got lost? So our t star, right? So this is just x bar plus or minus t star times our standard error. Okay, so we established our standard error is 0.0949. And then t star, if you look up 9 degrees of freedom, 95% confidence, you get 2.262. So here I get 5.2 plus or minus 0.215. And so that gives me 4.985 to 5.415. Okay, and then so the conclusion we make, we want to know, do we have evidence that it's different from 5 pounds? So we're going to say, is 5 in the interval? It's not 5.2. We're not asking is 5.2 in the interval, it's is 5 in the interval. Okay, and 5 is in the interval. So we do not have evidence that the mean weight of bags, mean weight of potato bags is different from 5 pounds.
So why do we ask if 5 is in the interval, not 5.2?
Because 5.2 will always be in the interval. 5.2 is our x bar, and x bar serves as the center of the interval, so that's always going to be in the interval. Okay, is the center of the interval in the interval? Yes, of course the center of the interval is in the interval. The question, so it's not, and we're not asking about is the sample mean in our interval. We want to know, does our interval provide evidence about the population, and could the population be this other value? So we want to know, is that other value inside the interval? Is that other value being 5? Is 5 a plausible value for the population mean? And it is in the interval, so yes. Yes.
I have a question about, is the interval in number 43 where it's 4.985 to 5.415, is that where the 5 is part of the interval?
Yeah, so you look at 5, and 5 is in between 4.985 and 5.415, okay? So if the question said, do we have evidence that it's different from 4 pounds? 4 is not in between those two numbers. So we do have evidence that the mean weight is different from 4, okay? Is that good?
Yes.
Okay, and then and we'll get to our, now we're at our last page of this stuff. Or wait, maybe not the last page, sorry. Wait, it is. It is the last page, okay. We're almost done. You guys aren't sad that the class is ending?
Dying on the inside.
I know, every quarter. Okay, last page now, all right, and it says a fair die should land showing the number 4 1/6 of the time, and you roll the die 100 times and you count how many times it lands as the number 4, and it lands the number 4 20 times. Does this mean, it's different? Okay, so we got proportions, and we have one sample. Okay, so our appropriate hypotheses, the null hypothesis, should be that that the proportion P is equal to what? Yeah, P is equal to 1/6, okay? Or if you want to put in decimal, 0.1667 or something like that. And then the alternative is that it's different. P is not equal to 1/6, okay? So you can leave them in decimal, or, P is not equal to 0.1667. All right, our sample proportion. So let's stuff our data. We've rolled it 100 times. We got 20 number 4s. So our p hat would be 0.2. So 46, that's easy, 0.2. Okay, 47, standard deviation of your sampling distribution. That's just another word for the standard error. Okay, that's the definition of the standard error. And so this is the square root. And because it's a hypothesis test, we're going to use P0 times 1 minus P0 over n. Okay, and so again, all of this detailed on the formula sheet and the study guide. So, here it says use the P0 for a hypothesis test, and over here it says use P hat for confidence intervals. So, yeah, so we're doing a hypothesis test. And then so here we're going to do, 1/6 times 1 minus 1/6, which is 5/6, right? Divided by n, which is 100. So what does that come out to be? 0.03727. Okay, and our test statistic z is going to be p hat minus p0 divided by our standard error, our p hat is 0.2. I'm going to subtract off for p0 1/6 divided by 0.03727. I get a z equal to 0.89, rounded off to 2 decimal places. Whoops.
Where did you get 5/6 from?
1 minus 1/6.
Oh.
Yeah. Fractions.
But you can also do it in decimal.
You can do it in decimal. Yeah. You can do it in decimal.
What did you say about P0?
When you do a hypothesis test, your standard error uses P0. Or, wait, no? That's not what I said? Okay. All right, so my z is 0.89, okay, and then so we would want to look up our p-value, okay? So we're going to look up 0.89, and we're going to do our tail area. Because z is positive, is going to be the area to the right of 0.89, okay? And so, here, the area to the left is 0.8944. So we do, 1 minus 0.89. Wait, no, I'm sorry. What am I doing? I look up 0.89. Okay, so I look up 0.89 and I get 0.8133. So 1 minus 0.8133 is 0.1867. And then my p-value is going to be 2 times that. So 2 times 0.1867 is 0.3734. Okay? So this is bigger than 5%. So do not reject the null hypothesis. And we would say we do not have evidence that the die rolls different from 1/6. We do not have evidence.
What's the two-sided hypothesis saying? What does that mean, basically?
Here we would be interested if it rolls the number 4 too many times, or if it rolls the number 4 not enough times. Okay? If it was one-sided, it would be we're only interested if the die rolls the number 4 too often. Or we're only interested if the die rolls the number 4 not enough. Okay? And here we're interested if either of those anomalies happen. Okay? So we don't have evidence that the die rolls the number 4 something other than 1/6 of the time. Is that good there? Okay. All right, let's look at these sampling methods. We're almost done. Okay, so we got Major League Baseball wishes to conduct a survey of its players. Instead of trying to create a list of all the players from all their teams, they decide to randomly select 4 of their 30 baseball teams, and they're going to select players on those teams. Okay, what's this? This is cluster sampling, right? Okay, and then a company wants to survey its employees. They take its master list of everyone and randomly select people. That's going to be SRS. And then number 52, they've got a toll bridge and they're going to stop every 10th car. Systematic. Great. I don't know how to. Systematic. Okay, great. Let's look at these other questions here. Okay, a bar chart is used for what kind of data?
Categorical.
Categorical. In a normal model, approximately what proportion of data are within 2 standard deviations of the mean?
95%.
95%. The intercept, huh? Yeah. The intercept in linear regression would be our predicted value when x has what value?
0.
When x is 0. The probability of A and B happening together is 0, then that means A and B are mutually exclusive. Oh, here I use quantitative, but that basically means numeric. For a numeric variable, if there's only one peak in the histogram, how would we describe the shape? Unimodal. Good. Which measure of center is not heavily influenced by extreme outliers? The median. Okay, I think that wraps it up. So we'll end a little bit early today. Good luck as you guys study. We'll see you guys next week. And yeah, it's been a pleasure. So.